welcome to the informal seminar for this week. We're super excited to be hosting Angelo Ricarte. Angelo is an expert in almost all things, if not all things, black holes, from modeling, so understanding from very small scales close down to the event horizon in terms of plasma dynamics and so on, and connections to jets, and also up to large scales in terms of how black holes influence their surroundings, influence galaxy evolution. He is involved in a variety of different proposal efforts for instruments. He has coordinated a whole bunch of work within the Event Horizon Telescope collaboration, including like polarimetric analyses, also kind of in future-looking EHT-like projects, black hole demographics. He is co-leads the theory working group. And in fact, we're both, we canceled theory working group for the EHT today.
Because it's right now.
Because it's normally right now. And so Angelo did his PhD at Yale, and now he's going to tell us a little bit about his recent work on strong magnetized black hole accretion flows, grid models, and so on, jet spin evolution, and new observation approach of these. So please, Angelo.
Thanks a lot, George. Yeah, so as you just heard, I'm Angelo Ricarte. I'll be telling you about work spanning event horizon scales from cosmological scales, the unifying theme being these magnetically arrested disks around supermassive black holes. What we have learned recently at the event horizon from EHT and GRRMHD simulations, and how this can connect with the cosmic evolution of supermassive black holes in terms of providing insights for fueling and feedback. If you're not a black hole person, you should know that we think every massive galaxy hosts a supermassive black hole at its center. And when a black hole accretes gas that is fueled from the galaxy, a gas heats up and causes it to shine as an active galactic nucleus or an AGN. If you want, you might call objects like Sagittarius star at the center of our galaxy or M87 a low luminosity AGN, but that's really kind of stretching the limits of what you might call an AGN, as these ones are extremely faint. This is an object that we've known about for a couple of decades due to the meticulous tracking of stars at the center of the galaxy. And as of last year, we now have this polarized image of Sagittarius star as well from the EHT. As George mentioned, I was the theory lead on that project, so if you have any tough questions about that image, feel free to shoot them at me. Nowadays, we can find black holes at the centers of galaxies when they are accreting across cosmic time out to about redshift of 10 or so now, due to GRRMHD. Now, the one at the center of our galaxy is pretty dormant, but other black holes make their presence a lot more felt in their host galaxy. Here's one called 3C348, or Hercules A. In red, you are seeing radio on top of this optical image, which reveals these jets that are shooting about 1 million light years in either direction. This is one form of what we call AGN feedback, which can take the form of jets, but also radiation or winds, depending on the system. And it's believed to be essential for galaxy evolution, especially the most massive galaxies like these. If you run a galaxy simulation that's supposed to turn into something like an elliptical galaxy, but you don't have a black hole, it will tend to actually just be some giant version of the Milky Way instead, which you never see in the universe. So these black holes are implicated for regulating the star formation rate and transforming the morphology of these galaxies as well. This is, typical picture of the central engine. Sometimes we have this relativistic jet, but not always. I'll be touching on that. And the most important properties that I'll be focusing on for the space-time are going to be the mass and the spin. And then for the accretion flow, you can imagine all kinds of different configurations for the accreting gas. But I'll be focusing on the accretion rate, just the total amount of material that's flowing in the disk, as well as the magnetic field, by which I mean both the geometric configuration and the overall strength of the magnetic field in terms of regulating the evolution of the material that is flowing in, as well as shooting out in the jet. Now, the overall challenge in terms of modeling all of this is that the dynamic range relevant for this problem is enormous. On event horizon scales, the sorts of simulations that we use, GRRMHD, are usually believable to maybe 100 GM over c squared, although of course there's a lot of local effort here, really pushing the boundary on that. However, we believe that AGN are connected to their overall environment on mega and sometimes gigaparsec scales. And it's completely impossible to treat all of this self-consistently in a single simulation. And so theorists have devised different techniques to tackle each part of this problem in separate frameworks. Where I started my PhD is on these larger scales, where you can study the connection between black holes and their host galaxies with semi-analytic models, which I'll talk about today, as well as cosmological simulations. But these will tend to peter out, well, the cosmological simulations will tend to peter out in resolution at maybe a few hundred parsecs, meaning that you still have a long way to go in order to really capture all of the relevant astrophysics. To really nail down this point, we're going to be zooming in on this galaxy, M87, whose black hole is featured at the bottom left here. And we have a scale bar that you probably can't read going 100,000 light years. And as we zoom in, we're going to be looking at different scales viewed through different telescopes at different wavelengths. We passed SDSS and Chandra, and now we're already at the Hubble Space Telescope, where you see this several kiloparsec scale jet emanating from the center at this wavelength. Here is a fruitful area where one can do dedicated simulations for individual galaxies. One typically, if you're not at Princeton, will reach a resolution of maybe sub-parsec or so, but people here have been going deeper. As we zoom in further, we're now kind of in this regime where you kind of have to bridge these scales. And this is often done with subgrid physics, we say, in cosmological simulations, where you try and stitch together the GRRMHD scales, what you might learn from accretion and feedback here with initial conditions that are up on those larger scales. And finally, we've reached the scales that we can directly compare with GRRMHD. The scale bar there now is 0.01 light years, telling us that even for the most massive black holes, like M87, which is 6.5 billion times the mass of the sun, you certainly need many techniques to probe all of these. So today we'll be looking at a couple of these different techniques that I've been working on, starting with the EHT and GRRMHD on these small scales, and then linking up with what we can infer from these to see what the cosmological implications of our inferences might be. If you're unfamiliar, the Event Horizon Telescope is a global millimeter wavelength array directly imaging black holes. Using a technique called very long baseline interferometry at a wavelength of 1 millimeter, we're achieving 20 microarcsecond resolution. And we actually just finished our most recent observing run this year, thanks in part to the observing efforts of your own George Wong, as well as many, at least I think 70-ish people observing in the past few weeks. But for the overall analysis, there are hundreds of people in the collaboration around the world performing different parts of the data reduction and analysis. That's two recent group photos in Mexico a year ago, capturing some subset of us. And this is, of course, it needs to be a kind of multinational effort due to the fact that we're located, our telescopes are located all around the world. The first image of the black hole was published in 2019 using 2017 data, and we've been making steady progress on this ever since. We now have 2 epochs on M87, which lets us probe the turbulence, the time variability of these systems. And I've been really focused on understanding these polarized images that you can see on the right here, because this allows us to break degeneracies and tells us about the magnetic field. These are interesting both for testing theories of black hole accretion and feedback, and also constraining any deviations from GR. GR is still doing okay, as you might guess. We're busy with many more years of fully polarized data including now some observations at 345 gigahertz that I'm excited about. So stay tuned as we continue to laboriously process all of this. But I wanted to focus on some of the results that are coming especially out of this polarized analysis, what we can learn about the accretion flow. There's a particular dichotomy that we like to focus on. It's probably a false dichotomy, but we like to compare and contrast these sorts of limits of a strong magnetic field that is governing the dynamics of the accretion flow versus one where the magnetic fields are subdominant to the gas pressure and basically just going along with the flow. This is called magnetically arrested disk, or MAD, for the strong field case, or standard and normal evolution, or sane, for the weaker field, which is something that I'll be referring to in upcoming slides. And so far, the EHT studies have been preferring this MAD case, actually. You can see effects of the magnetic field on this image here by George Wong in one of his papers a few years ago, where in the MAD case, the magnetic fields have caused there to be what we call flux eruption events that are energy injection from magnetic reconnection, giving us this, these big bubbles, and the accretion has to snake in through these very non-axisymmetric paths. Whereas the same case is more Smith. Now, the reason that the EHT tends to be preferring these MAD models is due to breaking degeneracies with polarization. There's a degeneracy if you want to match the total intensity between the density that you have and the magnetic field strength. You can dial either of those up to match the total flux that we see. Now, if you have polarization, however, there is a Faraday rotation that causes depolarization in the system that allows you to break degeneracies. So the MADs will tend to have lower densities and preserve more polarization than sanes. Typically, it depends on a lot of other parameters as well. And so in this talk, I'll be making this ansatz. What if strong magnetic fields are ubiquitous? What implications might this have on our understanding of accretion and feedback? And I think there are reasons why this is not an unreasonable assumption to make. At the very least, we ought to be making some testable predictions. First of all, MADs can arise from generic initial conditions, ranging from dedicated studies of Znajek star and M87 to magnetized bondi, to zoom-ins on quasar-like systems. It seems not unusual to get very strong magnetic fields. Observationally, AGN also follow fundamental planes, by which I mean relationships between things like black hole mass, the radioluminosity, and the X-ray. This more recent one from RUFA ties in millimeter as well, suggesting that maybe these AGN, especially at these lowest Eddington ratios, are not too dissimilar from each other. And these also give us an explanation for flares that the sanes are not able to provide. These magnetic flux eruptions that show up as holes in this millimeter video that I'm showing you, but can turn into hotspots that are implicated in flares in the X-ray and near-infrared, one of the leading models for that. What does it mean if magnetic fields at the MAD level are kind of typical? Well, first of all, for accretion, the magnetic fields are going to alter the disk geometry relative to, say, your typical thin disk that people will usually assume in a cosmological simulation, and will suppress the inflow rates. That second part is good for explaining observations of, say, M87, but could pose some interesting challenges for growing a black hole in a cosmological setting. In terms of feedback, the magnetic field is generating extremely efficient jets powered by spin extraction. That's called the Blandford-Znajek mechanism that I'll be talking about in a second. And in this plot on the right, I'm highlighting how polarization was really driving this conclusion. If you only have total intensity, the models that were appropriately matching M87 varied by orders of magnitude and accretion rate. Including polarization gave us a limit on what's called the Faraday rotation depth, and narrowed us down on a particular set of models at the lower accretion rate end, but with stronger magnetic fields.
Angelo,
Yeah.
why would magnetic field suppress the inflow and not enhance the inflow? Because I thought if something like the MRI is going on, then that would increase the accretion, right? So is there something else that you have in mind, or?
Yeah, so there are simulations, including those done by Ming-Hao Guo behind you, showing that, well, basically there's just extra magnetic pressure and, you know, like in this case, it's harder for this material to come in. This is a result from numerical simulations. So I was mentioning these strong jets that are coming out of the MAD systems. Here's a plot from Ramesh Narayan et al., including myself, back in 2022. And what you're looking at here is jet efficiency as a function of spin for a set of GRRMHD simulations, each of which is one of these black points. What you'll notice is that this eta, which is energy coming out divided by rest mass energy going in, can actually be over 100%. And this is because the jet is tapping into the spin energy of the black hole via this process that was predicted many decades ago. In their formulae, which was expanded analytically for low spins, the jet efficiency is proportional to the square of the black hole spin, as well as the square of the magnetic flux threading the horizon. And this is a magnetic analog of the Penrose process. A natural consequence of this is that if you power a jet like this for a long enough time, you're going to spin the black hole down. And this is something that we studied in this paper as well, in terms of this dimensionless spin up parameter. What you're seeing here is S as defined by the equation in the top right as a function of spin for our GRRMHD in red compared to the thin disk as that dashed line. A thin disk, and this is following equations that go back to Bardeen in 1970, will always have a positive S, meaning it's always trying to push your spin to a value of 1, where you have S equals 0. GRMHD, on the other hand, had the zero crossing that was just a little bit larger than 0, meaning that if you have a prograde black hole in this mad state, you're actually losing more angular momentum from the jet than you are gaining from the gas falling in through the disk. And an implication of that is shown here on the right, where I've just initialized a bunch of black holes at given spins and said, what if we follow this formula and have it accrete at this value, 3 times 10 to the minus 3 for a gig year? You can spin down a black hole that is initially at around 0.9 to more like 0.5 instead. And so this effect is slow, but could potentially affect black holes that accrete at a low rate for billions of years. And this is how we understand the black holes to behave in the most massive clusters in the universe. We call those maintenance mode AGF. Those galaxies assemble their stars earliest and then basically need to be prevented from making any more stars due to AGM feedback. We extended this in a later paper that I led in 2023, making the ansatz, what if Super-Eddington disks are mad as well? Here we analyzed 38 GRMHD simulations that included radiation. This was just an M1 scheme. And this was exploring a variety of different masses, spins, and accretion rates. Those two masses motivated by light and heavy seeds in the very early universe, which I'll touch on briefly at the end as well. I'll skip to the overall results, which is captured by the equilibrium spin as a function of Eddington ratio. And so far, what I'm showing you here is not interesting. It is just 1, if you are assuming a thin disk. And essentially, again, this is given by where that spin up parameter S is equal to 0. It's always 1 for this thin disk. We developed new subgrid formulae, continuously evolving based on our GRMHD simulations over here. We didn't have simulations on this side we think, this shouldn't be so abrupt, but in principle, more simulations could smooth that part out. And the point is that the equilibrium spin goes down anytime you have sufficient jets from the BZ mechanism, as long as your magnetic field is strong enough. So as I showed before, it's very close to zero in the hot accretion phase if your Eddington ratio is very low. And it gradually goes down in the Super-Eddington end as well. If you're interested, there are new, what one might call subgrid formulae that are usable for cosmological contexts. I know of at least one paper that has already done this. And this will also self-consistently give you the jet power. Interestingly, at an Eddington ratio of 1 or so, you get a jet power that is on order 10%, which could have some testable observational implications as well. Oh, and it's also at that value where the equilibrium spin has already gone down to around 0.8, which could have some implications for spin measurements that people have made as well. What I've done most recently is plug those formulae into a cosmological context. So here we're now moving to these larger scales. I have a semi-analytic model that's called Serotina, and this evolves black holes from the extremely early universe to the present day. Back in 2018, during my thesis, I wrote papers about how you can distinguish between seeding models at very high redshift using next generation facilities. We're now pushing into that redshift range with JWST. And the idea is to make some simplified assumptions about black hole galaxy coevolution, seeding, accretion, and dynamics, and then self-consistently produce a lot of observables at once to try and test the model against as many things as possible. In the era of large cosmological simulations, SAMs are still useful if you want to efficiently model large volumes and small halos simultaneously, making it especially suited for these seeding predictions. And I would say they're actually, from my perspective, getting more popular in the JWST era. They're also useful when you stop believing your cosmological simulation as much, which is becoming more of the case at extremely high redshift as well. So let me show you how this works, or at least one of these instantiations in action. What I'm showing you here is the evolution of black holes from the very early universe. I started at redshift of 20, and we're going to the present day on what's called the M-sigma relation, where M is the black hole mass, and sigma is the velocity dispersion of the stellar component of the galaxy. I have, by construction, made it so that these are going to move towards that relation as we go to redshift of 0 and match local observations. The new aspect that we added in recently was to add the spin evolution formulae from GRRMHD in order to make observational predictions for a variety of potential spin measurements. So if you're interested, we have predictions for comparing with X-ray reflection spectroscopy, spins that we could access with of objects we could access with EHT, as well as LISA. And I'll show you some of those in just a bit. First, we'll start with some simple examples. Here we have the most simplified case where I have sane accretion. That is, I'm just going to ignore the impact of magnetic fields. I'm also going to ignore any mergers. And so in this condition, the black hole is going to spin up to 1 and, or in this case, 0.998, which is a limit from Kip Thorne. And it's going to stay there. And this is what you see here in the spin panel, not terribly interesting. Serotina gives this prescription for what the accretion rate ought to be. And you can see that it is traversing all of these different regimes between Super-Eddington and highly Serotina as this thing is growing from the very early universe from a heavy seed to a supermassive black hole.
Just assume the angular momentum of the infalling gas is always the same?
Yes.
Cosmological.
Yeah. So this particular SAM, I don't have any spatial information. Yeah.
But you might expect the accretion is sort of chaotic.
Absolutely. Yeah. Yeah. I'll actually. So I'm going to put some examples of what happens there. One thing that could cause jumps in angular momentum are black hole mergers, which I ignored for this red set of curves. Again, I'm lacking spatial information, but I said, well, maybe if there's a black hole merger with a mass ratio of at least 5%, I'll say there's a 50% chance that you flip the angular momentum of the reservoir. And that could mean either the black hole spin has changed, or during that messy merger, the reservoir itself has changed its angular momentum. And in this case, you do see some jumps here.
Yeah. So, what are you actually doing to model the mergers?
So, yeah, there are fitting formulae that come from GR simulations, and I have used them as a function of mass ratio and individual spins. I randomize all of the relevant angles when I do that. And then I added on that extra thing. Well, if the mass ratio is high enough, maybe I'll flip it to retrograde sometimes.
So if I looking at the yellow, the spin plot, there 1, 2, 3, 4 mergers happening within the first sphere, or is this one and it's just?
There are at least 4 that are obvious, I would say. Anytime you see a discontinuity like these, so these are small ones that it looks like they didn't pass my mass ratio cut in terms of flipping, in this case, a retrograde to a prograde. But yeah.
And you're just randomly sampling for when these mergers happen?
So this comes from the merger tree itself. Yeah.
And why does it not go back to the third limit after the mergers?
In this case, it's because they just were not accreting anymore. So I've chosen the black hole. I've chosen an environment where this is a cluster 10 to the 14 solar mass halo. Yeah, as I mentioned before, they will tend to assemble early, and then you need your black holes into maintenance mode ever since then. And so it's at low enough Eddington ratio that neither the spin nor the mass are going to change too much.
Like displace the black hole from the center.
It could in principle. I'm not taking that into account. Okay. So what I've shown you so far, this is stuff that has been shown for decades prior. Marta Voluntari has some great papers on this, for example. The new element is to add the spin down from MAD BZ jets. And what you should be comparing is the orange versus blue, or in this case, now there's this gap. Because anytime that the black hole gets close to Eddington, the jet is starting to turn on, and it's going to limit the amount of angular momentum that you're getting. And it's not actually going quite up to the Thorne limit in this case, which can have some observational consequences. Going back to Jim's question. So far I had been assuming that the accretion is going to stay coherent. In purple now, I am testing out an incoherent case. And this is the limit where your reservoir is switching its angular momentum direction on very small timescales compared to the evolutionary timescale of the black hole. And so in this case, accretion is actually always pushing you towards 0, and black hole mergers are needed to give you any spin at all. This is an interesting model, both because we don't know really in detail how coherent these accretion flows actually should be. There are also observations that suggest that it's actually radio AGN that are most likely to be found in mergers. This might be a selection effect, but one proposed explanation is that you need the angular momentum from a black hole merger to give you a jet to give you the radio emission. So I mentioned you can do this for a population of objects and then test against some observations. There's been a growing literature in X-ray reflection spectroscopy, now including some X-ray polarimetry with XP as well, where there are about 55 spin measurements in the literature. Luckily, there had been recently a few reviews, so I collected them all together and turned them into a distribution. This black distribution is what you get if you just treat every point equally. there's been discussion in the literature about how more luminous objects are more likely to be in the sample, and more luminous objects will likely have higher spin because of the radiative efficiency. I had some way to try and take that into account, which gives you this red histogram instead. What you should see is that they are peaking at 1, but there's actually a sizable tail. I think in the past, measurements have been more strongly clustered towards 1 compared to where we are now. That said, there are still 0 claims of there ever being a retrograde system, which is interesting as well. And it's something that we can compare against. So what I did in Serotina is evolve many different halo masses from the dwarf galaxy regime to galaxy clusters, sample those each many times to probe cosmic variance as well. And this is what we get for the fiducial model. The reason my statistics here are now not great is because I'm selecting for Eddington ratios that would be selected in this kind of technique. So in the thin disk regime, and this actually matters, which I will show you in a bit. But the point is that the model with MADS, which is blue here, is kind of in between the observed biased versus debiased curves, which to me seems reasonable. We can now compare against different variants of the model. Perhaps most importantly is comparing the dark blue over here, which is the MAD fiducial, versus SANES. Again, that basically just means typical thin disks, which in this case are strongly clustered towards 1. That's actually much more obvious if you look at the sample as a whole. On the bottom, what I'm showing you is the distribution of objects on the spin mass plane. The stars are the ones that are high enough Eddington ratio to make it to the histogram up there. Most of them are at lower Eddington ratio. And you can see there's more of a difference in this cloud of points for MADs that are repelling things away from 1 compared to the SANES. Yeah, a couple interesting selection effects that show up here. Even though there do exist retrogrades in Serotina, which are given by the blue points, none of them are stars, meaning that if you were to have a system that was high enough Eddington ratio to be observed by this technique, the fact that you have a thin disk is actually going to bias you towards the envelopes of these spins. So in the MAD fiducial case, for example, if you start off retrograde, your thin disk is going to spin your black hole into a prograde system. And it's not necessarily representative of the underlying population. It's on the envelope. Interestingly, this incoherent model, where I'm flipping between prograde and retrograde on short timescales, appears to be extremely inconsistent with the data. However, I'll mention that this one has more reasonable predictions for jet powers in the integrated across the universe than this MAD one. So there might be an interesting tension there that I'd be interested in discussing. Okay, so I mentioned that if you look for bright sources, you're going to be biased. One way to get at the underlying population is to look at sources that are not necessarily accreting. So here are distributions of redshift mass and spin for black hole mergers that are detectable by LISA. I actually folded them through the sensitivity curve, kept anything that would be signal to noise 8 or greater, and weighted cosmologically appropriately. Here we see an interesting difference as well between different seeding models. I didn't mention this before, but we do not have a good understanding of how the very first black holes in the universe that become supermassive are initialized. And so we have rare and massive seeds that we call heavy on top, and then more common and lower mass seeds, light on the bottom. They're distinguishable in terms of their mass distributions here, almost by construction, where you have this deficit of objects over here that don't appear in the heavy seed model, but do appear in the light seed model. However, you cannot tell based on just these distributions how that mass was assembled. That information is encoded in the spin distributions. And in particular, I'll be really interested one day to know if if the peak is at 1, as one would expect from sane assembly, or if it's shifted over by some of them. And there are other interesting features of those curves I could talk to you about as well. So far I've said a lot about a particular set of MAD models. There are big questions in terms of how generalizable those are. Are all MADs actually the same? Is there a MAD duty cycle? Things of that nature. And so we need to keep testing this both observationally and theoretically.
Sorry, so here, how do you break degeneracy between massing and the directions of gas?
Yeah, so here there's no sense of prograde or retrograde because we're talking about the black region.
Yeah, I mean, the mass can lead to a low spin case, but random rotation of gas can also lead to a low spin case. Can you break degeneracy between these two?
Yeah, in principle. So I have both of those cases here. There are, of course, many assumptions that go into this. But for example, if we look at the bottom here, normal MAD is for light seeds is blue. Incoherent accretion switching between retrograde and prograde on very short timescales is purple. That is peaking at.
Assuming that the timescale is always much shorter than the
Yeah. And so one could concoct a model where there is some duty cycle that makes it, exactly lie on the blue curve. Yeah, but yeah, this is where we are. I would say. Mm-hmm.
Is there some argument as to why accretion has to be always mad or always sane, or should we expect that the black hole sometimes is doing one thing, sometimes the other thing, or that high redshift or red something? That ECD, I don't know, whatever. What should I think about that?
Yeah, I think it's very much an open question, and regarded both in terms of the observations and simulations, which sometimes show a duty cycle depending on your initial conditions. There's also a dichotomy in terms of radio quiet versus radio loud AGN. That might mean that you're not always mad, or that might mean that you don't always have sufficient spin, or that could be a selection effect. So I think there are a lot of questions here that are still unanswered. Love to discuss more about that with everybody. So I was transitioning to testing the MAD model. So far, I've made a lot of, I've done a lot based on 2 objects. I would be a lot more comfortable if we had a larger number than that. And so with the Black Hole Explorer, which is a proposed extension of the EHT into space, or soon to be proposed, we hope. We're waiting for the announcement of opportunity. But the preliminary one suggested that it would arrive this month, actually, and then we would submit in June. We have been, pushing forward, assuming that this is going to happen. My point here is that we have different resolutions here on the bottom. And these objects are all to scale in terms of angular size. So you can see that EHT, especially in 2017, would not be able to resolve the shadows of any of these except for M87. But the BHEX resolution certainly can. And so we intend to do the same sorts of analyses that we've done for M87 and Sagittarius Star with these other objects as well in the 2030s, if this mission actually happens, as well as get precise photon ring spin measurements of M87, probably Sagittarius Star, depending on details of the orbit and how we can mitigate scattering. So, in addition to that, I want to, with the last amount of time that I have, talk about recent tests that I performed in the time domain. This is something that the EHT is moving towards. I would say our next milestone is likely to be characterizing better the dynamics of both Sagittarius Star and M87. Here what I'm showing you is a movie from Nick Conroy et al. 2023. They characterize what they call the pattern speed. So basically, if you're following some overdensity in emission, how rapidly is that rotating around the image. And it turns out that they found this relationship mostly encoding the disk inclination, not the black hole spin inclination, which is also interesting. And then you could have a difference between MADs and states. So this is just one quantity that one could calculate out of a movie that we could potentially produce in order to continue testing these models. But imaging even a single epoch is hard. Making a movie is much harder. I was recently a polarimetry working group coordinator as well. And so it was interesting to me to explore if we could substitute polarization for spatial resolution and get away with much easier observations and data reduction. So this is a recent paper that I looked into, I put on the archive a couple of weeks ago about using what are called QU loops in order to probe the dynamics. Okay, so this is a bit technical. Let me walk you through this. For linear polarization, Q and U are the basis that we like to use for this, what are called the Stokes parameters. Q gives you this cross mode, U gives you this X mode if you fix some basis. And it turns out that if you stare at Sagittarius star, and this is particularly obvious around a flare, you will get what's called a QU loop if you plot Q and U as a function of time. This is a set of observations from Vilgas et al. 2022. And if I just use this cursor to go around, it's going like this. Suggesting that there's something clockwise in the dynamics that's getting imprinted on the polarization, even if you can't actually spatially resolve what's going on.
The points are what I should look at.
Yeah, so those are ALMA observations.
There's like more than one.
Yep.
There's an inner ring also at some color.
Yes. Mm. Yeah, so the usual explanation of this has been a hotspot model. The gravity collaboration has also seen many of these, as well as associated centroid motion, even if they can't resolve the whole thing. The explanation is that, well, imagine you have some hotspot in a rotationally symmetric magnetic field, and it's more or less face-on, not too edge-on. Then that hotspot is going to be selectively illuminating parts of the magnetic field and imparting the geometry of that patch on the polarization. It turns out this naturally gives you a QU loop. But after staring at GRRMHD for a very long time, I never saw anything like that, but actually always saw ubiquitous QU looping behavior if you make movies of them. Here's an example. This is one of the models that is in our ngEHT library. When we did our analysis of Sagittarius star, I picked an interesting and particularly clear one, which is pretty face-on MAD. I guess mostly don't worry about the parameters. But the point is that we have ubiquitous QU looping behavior without invoking any kind of hotspot. And if this is something you're interested in, this is purely thermal as well. There's no invoking of non-thermal behavior.
What's happening when the thing starts doing in the little loops?
Sorry, you mean the loops on this side?
Yeah, something like this, and then it stays at one point and then the little loop.
Yeah, I think that, so it's natural for even kind of macroscopic features to sometimes make one big loop and then one tiny loop. If you work out the ray tracing in even a simple hotspot model. So I think that's likely what's typically going on. There are also in this case, multiple components if one were to break this movie up into different pieces. So it could be that there was some small polarized patch giving you a little bit of a loop as well. Mm-hmm.
Slightly technical question. Is this more prominent if R high is small?
A little bit, certainly by eye, but I will show you a plot with as a function of R high in a bit. Yeah, so one needs some way to characterize this. You can ask me if you're interested in the details, but I used some differential geometry of planar curves to get you the rotation rate, applying this to both the data and the simulations. The real data look like this. I showed you this panel previously, and there are several papers talking about those obvious loops that are happening there. The days that were imaged by the EHT and in the millimeter look like that instead. And I looked at that and said, well, I actually think those are, quantifiable. It's not a complete mess. You can fit some splines to these and try and get a characteristic rotation rate. And doing so, I actually got consistent results across all of these different days. What I'm showing you here is the rotation rate in degrees per TG, which is GM over C cubed, which is 20 seconds for Sagittarius star. And this is a signed quantity, where negative is telling us we have a clockwise motion with my conventions, and in this case, about 1 loop per 30 minutes or so on average. Now you have to basically coherently average all of the random motions in some particular way. On the famously loopy day, the fraction of scans by ALMA that were clockwise is larger, and so it's more obvious by eye. But actually, I get pretty consistent numbers across all of these days. This is really interesting because this is now the exact same days that we observed with EHT and made this image of, and it breaks degeneracies in an interesting way as well. If you look at our theoretical analysis, one thing that flummoxed us was the fact that we observed what's called a rotation measure. So this is a change in the angle of the polarization as a function of lambda squared, where lambda is the wavelength. And if you interpreted this measurement as an external Faraday screen, that meant we ought to have derotated the image by 46 degrees. And it's only by doing that we actually recovered clockwise motion, which is what we expected indirectly from other analyses. Now that we have this measurement from the exact same days, this gives us much stronger evidence that it is this picture that is likely more correct. This is the only model where this is the only kind of analysis pipeline where we ended up with what we called a best bet model as well.
So can I ask, the picture has many Qs and Us depending on where you're looking at. Then the other plot, the loop was just one Q and U. Which one was it? How did you do that? And also these pictures come from some interferometer, so the overall average, have. So what was plotted before?
Okay, so
the loop is a what?
Yeah, the loops here are spatially unresolved. So this is ALMA only. You just see Sagittarius star as a point source.
Oh, so this is not from. Well, yeah, it is. So.
Well, yeah, it is interferometry, but treated as a single dish. Yeah. Yeah. So the point is that even if you can resolve the source and see the dynamics directly, you're actually able to get this dynamical information out of the polarization. And this was so in the case of this derotation, you want to do this uniformly across the entire image, which is what is shown here. What he ended up doing was taking that average QU rotation rate, applying this as a constraint, and comparing what we get with all of the models as well. So here we have MADS on top, SANES on the bottom, 5 different spins. You were asked about R high, George. Those are the different colors here. As typically, more of a sensitivity for SANES than for MADS. And it turns out that face-on MADS, like what we called the best bet model in our analyses, are passing naturally. They're lying right at the center of that range. Okay. So I've sped through the end a little bit, but I should wrap up. We've discussed the implications of strong magnetic fields, both at the event horizon and cosmological scales. Strong magnetic fields, what we often call MAD, are favored in EHT studies. And running with this insight, we have developed new formulae for jets and spin evolution. bridging those scales, we find that the BZ mechanism moderates spins at both very high and very low accretion rates. And that can show up in different observational samples if you are able to measure spin. We need to continue to test accretion flow models, both observationally and theoretically. And a lot of the questions that were raised in terms of, are all black holes actually mad and are all mass the same, are very interesting and can have some testable implications if we crank this through an observational framework as well. Given a mad model, my spin prior for MAD7 is on the bottom, going through Serotina. So I don't think it should be near 1 because BZ would have spun it down a little bit, except unless there was a very recent gas-rich merger. Not near 0 either, because, well, certainly you wouldn't have a BZ jet. But somewhere in between, either prograde or retrograde would be fine, which is almost all. All right, thank you, and I'll take any more questions.
So we do have some time for questions. I want to start. So on the previous slide where you showed versus inclination, and also looking at versus RI10, it looks like sometimes the radiation can increase at intermediate inclinations. Like, so for example, I'm looking at A minus 0.5 top panel, the blue goes up before going down.
Yeah.
Is that weird? That seems weird to me.
Yeah, I mean, I think that this is likely a case of just the emission region itself changing in some non-obvious way. I didn't actually mention this, but the typical trend is that the rotation rate will go down as you increase Rhi. This is basically due to noise from Faraday rotation. So I showed you this nice clean curve in a movie, but with Rhi 160, it's often a lot rattier. You'll get some random little counterclockwise loops that will cancel out some of your clockwise loops.
Sorry, what is this R high?
Yeah, this is a prescription that we use in the EHT to modulate the electron temperature. So yeah, we need the electron temperature to ray trace, but we don't think the ions and electrons are in equilibrium. So we have this large ratio between ion and electron temperature up to 160. It turns out these very large ones tend to do the best. We don't understand why that is, we understand that it's observationally due to depolarization usually, but simulations that actually treat heating and cooling will tend to get much more moderate values. So there's a little bit of a puzzle there.
This is a drop in temperature.
Yes. Yeah, that's another interesting area of exploration.
So is this omega basically some orbital frequency? What is it? Like what is the order of magnitude given by that?
Kind of. So yeah, I had a skip slide here.
You
So
also know the mass of the Znajek star. This went in.
yeah.
Your prediction.
Right. Okay. So actually, what I really should have said is no. So first of all, what I'm showing you here is the polarization QU loop speed. This is the total intensity pattern speed. So if you just make a movie and follow a blob, how fast is that rotating? So first of all, that actually does not follow the orbital speed either. There's just, we think pressure waves that are causing some overdensity in what
Roughly
ends up.
speaking, yes, it's
Yeah.
true. When you say it doesn't follow, it's like some 20% difference or.
I think factors of a few. Yeah.
Yeah.
Yeah. Yeah. And then, yeah, an interesting thing that we saw here is that there's a nice linear relationship between total intensity and polarization loop speeds. I wasn't expecting a nice linear one, but also the slope is kind of weird. So we got 4 and 2.7 if you do a best fit line. Our explanation is that as long as you don't have a single hotspot and there are just multiple components, you can end up with each of those individual components giving you a loop, whereas you have the same pattern speed for all of them. And the simulations, for some reason, will tend to give, it turns out you need 3 instead of 4 emitters for MADS typically, and some smaller number for SANs, but we don't fully understand that.
I guess the usual question that would be asked now, and I should ask it, is X-ray binaries. They don't necessarily show jets. So what's thinking about? They're the other obvious accreting black hole systems that we can probe observationally, and jets do appear, but very rarely. So
yeah, and they tend to have very high spins from especially X-ray spectropolarimetry now.
yes, well, the diagnostic used to measure the spin shows high, but it's not necessarily true.
Yeah.
Um,
I don't have a probably satisfactory answer. That may suggest that there's something special about those initial conditions, I would say, that are reducing the magnetic flux. I don't know if there's also, additional factors that need to go into making that jet observable. But yeah, I don't do too much on the small black holes.
Right.
If there are no other questions, then maybe I'll just close by saying, one, there's I think a few spots still available to meet with Angelo. Also
Plenty of them.
Tomorrow morning. And there's also a few spots for dinner if you want to join. We haven't decided where to go yet. So if you want to go to a particular place, and it's let us know. Okay, and with that, maybe we'll thank Angelo again for stopping.